Hello everyone. In this MATLAB demonstration, I'm going to explain how you can obtain the solution of the difference equation. I have considered two cases. One is a simple one wherein you can just tweak around with various values and then obtain the solution. A little one, next one is a little complicated than that, and for both I shall try to show you the comparison between the manual calculation and the MATLAB simulated version. The difference equation that I have considered is y of n is equal to 2 into y of n minus 1 plus 2x of n. You can see that the initial condition is given as 1, and the input is given as 0.5 un. That means it's just constant times a step input. So if you were to apply the unilateral z transform on this, you will get y of z plus equal to 2 into unilateral z transform of y of n minus 1 is y of minus 1 plus z inverse y of z. So you get this plus 2 into x of z. So you will get like this. But what is the z x of z? X of n is a constant into u of n. So you can recall from z transforms that the z transform of u of n is 1 by 1 minus z inverse. So you can write it in that way. So this becomes constant here. So 2 into 0.5. 2 is the coefficient of the x of n. So no matter what is x of n, the coefficient is 2. So that is 2 as it is. And x of n happens to be 0.5 u of n. So you can write it this way. And also y of minus 1 is 1. So I have just tried to substitute various values and then simplify this. So you will get a constant here and then 2 times z inverse y of z, though this term and this term are having y of z. So you can take that to the left hand side. On the right hand side you will be left out with the 2 plus 2 and half is 1. So this term on the right hand side, this term on the left hand side. I have tried to further simplify it, and you will get uh, so y of z equal into 1 minus 2 z inverse equal to this whole thing, and you can bring that 1 minus 2 z inverse on the other side. So you will get this will be the expression, and further you can so if you want the solution that is in y of n, that is in time domain, so you'll have to correspondingly take the inverse z transform of this, and for that obviously you require to find the partial fraction expansion, bring it into some suitable form wherein you can find the inverses directly. Okay, so I have expanded it and I have to find a and b, and you can in simple terms show that a is 4 and b is minus 1. So if you were to substitute that, you will get an expression like this. So this is so compared to this expression, the same y of z can be represented this way. This is more handy. This is more easy to obtain the inverse z transform of this. So when you apply inverse z transform, you will get yeah, taking inverse z transform, you will get the solution as y of n equal to 4 into 2 raised to n minus 1 u of n. So this is one solution. This is the solution. Next one, what I have done is, instead of taking x of n as a 0.5 u of n, I have made it 0.5 raised to n u of n. So instead of the previous example where always u of n is always 1, so always it was half u of n. That means from the 0 n equal to 0 to n equal to infinity, it was always half. So now what I have done is I have taken it as 0.5 raised to n. So its value keeps gradually decreasing this way, and for this kind of a signal, what is the solution of this particular difference equation. So initial condition remains the same. So you can see this one. Yeah, yeah. This part is not there. This part, applying unilateral Z transform, I think this is not the thing. So it should have been, yeah, it's over here. So let's remove this. Yeah. So y of z is equal to 2 into 1 plus 2 z inverse y of z, all that same. And only you can see the x of z value. X of z will be now 1 by 1 minus a raised to n, a u of n, isn't it? So it is of the form a raised to n u of n. So you can write it as this form. So you can see the difference. Earlier it was 0.5 here, now 0.5 is over here. So you can check the type of the signal. So what is the Z transform if it is a raised to n u of n, and if it is just a u of n, you can compare, you will get to know it better. And further you can simplify, and you will get an expression for y of z. This is the expression for y of z. Numerator and denominator you have in terms of z. So you can using partial fraction expansion, you can expand it like this, so that you get a smaller chunk which you can directly find the inverse. So this is a and b have been found out, and when you take the inverse of this expression, you will get the expression like this. So you can write it as it is of the form constant divided by 1 minus a z inverse. So its inverse z transform is 14 by 3, this constant as it is, a raised to n u of n. So if you apply z transform to this, you will get this, and vice versa. So this is our expression. U of n I have taken constant, common factor outside. So this is the expression for the output y of n. So given a transfer function, given a difference equation, you should be able to apply z transform, especially this unilateral z transform, and then obtain y of n. That will be the solution. So this is an elegant solution. Reason is, you can find the value. You can substitute n equal to any value. Say for example, n is equal to 25, n is equal to 30, n is equal to 70, 75, 80, 100, 1000. So you can substitute that value, and you will get the corresponding value at that time instant. Okay. Unlike the recursive type of solution, you need to know the previous value. For example, if you are recursively, if you are trying to find the solution of y of n, then to find the second value of y, that is y of 2, you have to know y of 1. Or if you want to know y of 100, you should know y of 99. Then if you have to calculate y of 99, then you should know y of 98. Then you will eventually require y of 97, and so on. So all values will be required. But this expression, you can just plug in the value of n equal to 75 or 100 or 1000 into this, and it will give you the corresponding solution. Okay. So this is the expression. This is the expression I have got it. And if you were to substitute n equal to 0, 1, 2, 3, and so on, I'll get this values like this. Okay, this is the example that has been considered. Now the same thing, if you were to demonstrate on MATLAB, you are going to use a built-in function, and we can because the other way we have already obtained the solution in the first experiment over there, so that you can recall even that also from your records. So the first two three statements are all known to you. Then you are asking the user to input the coefficients. Okay, so you have to input the coefficients of a numerator and denominator. So you have to make a matrix, and you're going to give the inputs over there. Then initial condition like y of n was there. So what is y of -1, y of -2, and so on. So you're going to give the solution over there also. So you can input the initial condition, and here how many samples you want to calculate. Say for example you want five answers, sorry, five samples in the output. See, 1, 2, 3, 4, 5. So if you want 25 or 100, so you can enter that values for just that is for comparison. You can do the comparison of your solution and the value returned by the MATLAB. Okay, and you're going to create a variable called n. So all activities, all calculations will be happening at these values. So it basically again depends on how many samples you wanted. So if you wanted five samples, what I have considered is from 0 to 5. So there will be actually six values calculated over here. Maybe you can subtract one over here, so doesn't matter. Okay, so next is this is how I have created the signal x of n. So here I have to create the signal. What was the signal? I'm going to consider the second example. It will be 0.5 raised to n u of n. So this is written as this fashion. I have written 1 by 2. You can even directly key in zero point 0.5 also. So that doesn't matter. So 0.5 raised to n. Now zero point 0.5 and n is now a vector. It's a matrix over here. So it is not a constant. Okay. So if it is not a constant, then if it has many values, then half raised to all of that will have to be raised. So you have to actually use the dot cap notation. Okay, yeah. Now this is the main two functions that we are going to use. Filt IC is one inbuilt function which is going to use the numerator coefficient and denominator coefficient and the initial condition that you have given. Okay, so this particular function uh, calculates something called zi. Okay, so this is required by the next function which is the filter function. Okay, so zi is required for this function, which is also inbuilt function. This is filtering this one, numerator coefficient and denominator coefficient. This is the actual transfer function. Using this transfer function, it is filtering the input signal x that you are creating over here. Okay, it can be any other signal also. You can read in some other signal and you can filter. So this this is the filter. It is filtering this with the required. This is the initial conditions, which is actually um, required for operating this filter. So this will be calculated by filt IC. So first you have to calculate this and then use that in the filter function to obtain your result y of n. Okay, and as I shown you previously, the expression output expression was 14 by 3 into 2 raised to n minus 2 by 3 into half raised to n u of n. That I have keyed in over here. 14 by 3 into 2 raised to n minus 2 by 3 into half raised to n. So this is you don't have to actually write this 19th expression here, 19th line. I have written it for the simple reason that I can plot the two and visualize whether they are different or they are same. Okay, and if 18th one is if this will be the output, it will be like 4 into 2 raised to n minus 1 u of n for the case 0.5 raised to n, the first example that I had shown. Okay, let us execute and see the result. Okay, I'm pressing on the run command over here, and it is asking me then enter the coefficients of x. So I'm going to, what are the coefficients? It's only two x of n was there, and y was 1 comma minus 2, and the initial condition I'm giving 1. So you can see the two results, and that is one is y, which is returned by the MATLAB, and this is ym, which is calculated. Okay, I shall show it again. initial condition, I'll give 1, and you can see the plot here. So output is continuously increasing, so it looks mostly like an unstable system. But anyways, there is only one plot because both the plots are overlapping one another. They are perfectly matching. You can see y. This is the output. Y is the output given by the MATLAB. This is the output as per my calculation. Okay, so 4 samples are calculated. Let us make it say 50 samples. So then also you will get this is the value, and this is the coefficients of denominator, and initial conditions there were only one. Yeah, this. Okay. Now this is how, if at all, if you were to uh, give initial condition as little different, then you will see the difference between the two plots. Okay, so I'm going to again execute this with a different value. Initial condition, I was supposed to enter 1. Suppose I'll enter say -1. Okay, yeah, you can see here the two, there is a difference here between the two signals over here. Okay, this way you can find the uh, using MATLAB. This is filtic. Is the filtic and filter are the two important functions over here. The and we are asking the user to input the values. So correctly, the input will have to be entered, and you can also see the sequence in which the all the data has to be provided. So if you were to interchange the numerator coefficient and denominator coefficient, again the result, corresponding result will be erroneous. So this is our reference for you to conduct this experiment on MATLAB, and you can write the record of this one, and maybe take some other difference equation, try solving it, and the same you give as an input to this program, and compare the results. Okay, so if there is any doubt or other requirements, you can definitely post the question in the WhatsApp group, or even you can text me. Okay, thank you everyone.